telling you about in the next 15 minutes or so is the topology detection component. And if we have additional time, maybe I'll do a review of the test harness, maybe not. So first place we're going to go is in network. So Pyretic core network. And I'll make this text slightly larger again so you can see it. So some things that exist in the network. And these could potentially be moved, actually. An IP prefix, an IP address, these might be better put in packet. I'm thinking about moving them. But what is important is starting on line 190, where it says tools. We have the first topologic construct. So this thing is a port. And what is a port? Well, a port is an object which contains a port number, a configuration, a status, and the port that's at the other end of this link, if that port is known. Now, this is a lot of data. We don't necessarily need to keep all of it, but because of the vagaries of doing port detection and some bugs which are common, if not prevalent, among switches in misreporting their status. We have a somewhat complex logic right now implemented. So one of these is ports claiming they're up when they're actually down, and down when they're actually up, and so forth. So what is configuration? So configuration is whether so what you can do is you can control the ports on a switch through the switch configuration utility, and set them to be off or on. And that configuration may or may not stick. But so we want to record what the reported configuration of the port is, what the reported status of the switch is, because if I've configured it to be on, it might still be down. Which is normal. Yeah, they're two independent things. And this link to just tells us what's at the other end of the link. And so there's a bit of fuzzy logic I put in here. Is the port definitely down? Is it possibly up? Etc. This logic isn't robust enough and probably should be gotten rid of. I have not overhauled the topology code in a long time. But this is kind of how I did it at the time that I did it last. And a location is simply a switch and a port number. So now we've got ports and we've got locations, and on line 237, we actually have the topology object. And this is the primary thing that's in a network, but we'll see what else is in a network shortly. So the topology object is just a type of graph. And if I open up another tab, do you see the tab on your screens? Okay, great. So is the name of a very nice library for doing networks stuff. It provides tools for making graphs, visual graphs of networks. It provides all sorts of generators for classical graphs, random graphs, synthetic networks, standard graph algorithms, et cetera, et cetera, et cetera. It's very hardened, very tested, very nice, and it's what we use. So now I'm going to switch back to say, okay, topology is basically a descendant of network X graph, so it inherits all the methods that you get, but it also defines some of its own. So there's equality. So we basically, have the idea of what is a node match and what is an edge match. And then if we want to determine if two graphs are the same as, two topologies are the same as one another, we actually do an isomorphism test on them using these quality comparators. That's, a little expensive, but it gives you, so for small graphs, this is doable. I wouldn't necessarily recommend doing equality tests on very large graphs. At least not this equality test. Add switch, so we can add.
So I asked you this yesterday.
Sure.
Who calls this and like what?
So if it's all right, what I'm going to do is, for right now, I'm going to tell you just about how the topology works.
Okay.
Very high level. The topology is embedded in the network object, and the network object manipulates and provides access to the topology.
Yes. Okay.
Okay.
Yeah.
So with that, their methods for adding switches, adding ports, adding links, determining if the network itself is connected or if it's partitioned. Calculating things like egress locations. And egress locations are going to be basically those ports that are possibly up, whose port link on the other side is none. So we haven't actually found another port. So that means it's exiting the network, either to an end host or to something outside our controller's view. Now, while the controller is learning the topology for the first time, the concrete network object is getting these messages from OpenFlow and using that to update the topology. You can have transient states where links actually in the network will be ports that actually are just internal to the network will be listed as egresses. But after a quick phase of convergence, that should no longer happen. And doesn't in the code for the last couple of months I've been using it. So it works reasonably well. It's not provably correct.
Is there a switch object
that I'm aware of? No, switches are just indexed by their integer.
Oh.
Yeah, because, yeah, we just use integer representations right now. So they're egress locations, interior locations, which are kind of the set complement of egress locations. Some stuff with copying attributes. So when you take a look at, this is a network. And actually, I'll just take a moment to wave with my hands. So those of you who are watching won't really be able to see this. But imagine a triangle. Okay, so we have a network triangle. It has one node, a link to a second node, a link to a third node. And the second and third nodes are also connected to a link. So this is your triangle. Now, that's an abstract topology, and I can run a variety of different graph algorithms on it, which will produce sensible results if I think of each of these nodes as being a switch. However, what's not taken into account is the fact that, hey, each link, the link between switch 1 and switch 2, actually has two named ports. Maybe it's port 1 on switch 1 and port 1 on switch 2. Maybe the names are something else. But your typical graph doesn't take this into account. So there are two potential design choices, at least, that seem obvious. One, you could imagine doing an extended graph. So actually, every switch has links to each of its ports, a different type of node, that then have links to another port node, which have links to a switch node. So we've got kind of this now extended graph where both switches and ports are nodes, just of different types. However, if you want to run graph algorithms on that efficiently, you've now made your graph much larger. So embedding that information directly in the graphical structure carries certain costs that we didn't want to take. So instead what we did was we provided attributes to various features of the graph. So each switch has a set of ports that is the ports attribute of that switch. And each link also has a dictionary, which basically has the name, maps the switch name on either side of it to the port. And it's not ordered because the link is bidirectional. By default, we use bidirectional links.
What is this?
So,
some data structure?
yeah. So basically, in a network X graphs, you have nodes and then you have links. And so what we do is we annotate the entire graphical structure
with
port information.
Nodes, and then, with port.
Port information, because the port information is missing.
Edge has like a switch and then a port.
Exactly. So every link or every edge in the graph has a dictionary that maps, that provides the keys, the two switch names.
Network X construct?
Yes, that is a network X construct. So basically a lot of what creates a bit of confusion here is the fact that if you want to do things like figure out ports, you actually now have to access these attributes.
Exactly.
Whereas if we had done the other encoding, it would all just be there. You wouldn't have to worry. All you'd have to access is just the type of the node, but at the cost of losing losing efficiency on doing your graph algorithms, which is not something we wanted to do. So in the end, we went with this slightly more cumbersome. And this is the same design choice that was made in POX. I think it was a good design choice. So if you want to get the attribute information generally you do something like on line 286, where you say, hey, all nodes, we're going to get the set of nodes, and we're going to set data equal to true. When you set data equal to true, that not only gives you every node or switch in the network, but also the metadata associated with that switch. And then you can access that metadata and use it for a variety of ways, a variety of things. So this copy attributes and reconcile attributes are basically used when I use a graph copy. For whatever reason, NetworkX doesn't always copy the attribute data, especially if I run the graph algorithm on it. It may or may not copy the attribute data, and the copied attribute data, since the graph's actually changed, may no longer be correct. And so all of this is logic to make sure the attributes, these attribute data, namely the port metadata associated with the topology, is always correct.
When you say all this logic, which logic is?
That's copy attributes on line 284, reconcile attributes on line 314.
So, okay. Initial spot, okay. So what is this? Okay. Data, what's that?
So data is something that's built into NetworkX. It's a built-in variable, and when I say data equals true, it means don't just give me the edges as a list or as a generator. Don't just give me the nodes as a generator, but give me the edges paired with their metadata. Or give me the nodes paired with their metadata, or attributes, whichever you want to call it. And this is the place where the port information is. And so, we have some things for filtering nodes. That's nice for doing a difference. So here we can see how copy attributes and reconcile attributes are used. So if we want to take the difference of two topologies to compare maybe how networks changed over time, or to compare two, network topologies that are just random, we got them somehow. So what we're going to do is we're going to try to use this class, which is a descendant of NetworkX. So we're going to use the NetworkX. We're going to create a new instance of the class, which is the result populated by the result networkx.difference, so the difference method defined by this NetworkX library of topology 1 and topology 2. And then we get a new thing out. And if the number of edges in that thing is 0, well, let's return nothing, because a graph with switches that have no edges between them is useless to us. That's line 354. And then, so we did do the difference, but the difference, however it's represented, doesn't necessarily have all of the attributes. So it might contain a switch, right? But the switch no longer has all the ports, because some ports, were in both, or weren't in both, or whatever. So we first copy all the attributes from topo 1, and the self, so we assign self's the new thing. So we do self and copy the attributes of the first topology. This is the bigger topology, because this is an asymmetric set difference. So we know that at maximum, it's going to be topo 1. It might be something smaller. So we copy all of topo 1's attributes onto our new result, and then we do a reconciliation of the attributes. Using the original topo 1 and comparing ourselves to topo 1, because we're obviously different now, unless topo 2 was none, or something trivially 0. And then we finally can return ourselves, knowing that what we've returned not only is the difference in terms of the NetworkX library, but has all of the annotated port information correctly provided. And so likewise for minimum spanning tree. If we want to calculate the minimum spanning tree, well, we're using NetworkX's minimum spanning tree, which is deterministic in nature, which is really nice. So every time you test it, it will behave the same, unlike perhaps using flood, where its behavior might change. But the attributes still aren't there. The minimum spanning tree is probably thinned out. So we need to go copy over the attributes since we lost them all, because NetworkX doesn't copy attributes, and then we need to do the reconciliation again. And then we can finally return ourselves. There's a randomized minimum spanning tree if you want. There's this disjoint minimum spanning tree set that I implemented that is a heuristic that lets you make a couple of different minimum spanning trees, all of which don't use the same links. So no two of which contain any link that's the same. So if you want to say do kind of some kind of semi-efficient, multicast, or whatever, you can, set up a couple of independent minimum spanning trees and get more out of your network.
So you mentioned this.
Sure.
Minimum spanning tree is what? This is the one you call.
Minimum spanning tree, yeah, is what Flood calls.
Now, difference. You said you might want to take the difference between two possibilities. Do you have a policy now that uses it? I'm just curious.
Oh gosh, I don't know off the top. I would have to do a regex search through. Yeah, at some point we did. We had like some use for it.
Anyway.
I think if you had a policy where you wanted to kind of isolate what the change was, right? Because what we give you is you kind of say, oh, here's a new topology. So if I was like, let's say I want to write a method that printed what the change was each time. So I would write a method that, so first it would, and each set network, it would store it would take the old one and it would take the current one and copy it to like a previous variable. Then it would set the current one to the new value that was provided by set network. Then you would take the difference and print the difference out. And that would show you the change to the topology. So that's like one simple application. You could imagine potentially doing things algorithmically with your routing based on changes. Like you saw a particular link goes down, oh, now I want to remap my flows, whatever. So a bunch of other stuff, all pair shortest path routing. You want to do that? Well, that's a class method that's provided in here. What? Yeah, this is handy.
What does that do? It gives you like
what
does that do actually?
It literally provides you with a data structure that describes the shortest. So when you put in any two nodes, so let's say you put in switch 3 and switch 5.
Does it recompute this every time you call it?
Each time you call it, it recomputes.
Okay, so I basically want to call this once and then pull out a data structure.
You want to call it once for each topology change.
Right.
Yeah. But then you keep the location path data structure it returns.
This is pretty handy.
Yeah, basically if you look on line 406, this is how you access it. You take the location paths thing, you put in one switch, you put in another, and then it would give you the path. That's the shortest path in the network. So you can very easily from this generate shortest path, all pair shortest path routing. And I used to have an example of that, and I don't right now. But one of you should write it.
This is going to be very useful with many things.
Yeah, it's really useful.
NFV, like the middle box stuff, like steering through.
Yeah.
You want to basically put a box. You want to basically know the shortest path to that box.
Yep.
And the shortest path out.
Yep.
So this is highly useful.
So other things you could potentially do here is NetworkX provides all pairs weighted shortest path. So if you were to say collect some information about traffic load, and you wanted to kind of reweight things or something, you could imagine adding some of your own annotation, copying the network object, topology object, annotating it with some info, then rerunning an algorithm from NetworkX. To that kind of end. So this just gives you a taste. These are kind of what I thought were common important things to kind of have in there built in, but it also gives you examples of exactly how you would, with NetworkX and with the helper functions I provided, do this kind of stuff. Now there's also a representation which shows you, okay, how do we print out the network? And so if you look on line 417, basically we say for each switch in self.nodes, what we're going to do is basically get the edge string that corresponds to the switch. So set the edge string corresponding to the switch to be a bunch of different edges, where we take out every edge in self.edges where data is true, in which the S1 and S2, the two switches that were on that edge, so where the switch that we're looking at currently is one of those two switches, right? And likewise, and we kind of go through this, and so you can look through this code, and it kind of provides an implicit but very poor documentation. Well, very accurate, but very difficult to digest documentation on exactly the format that's being used for the attribute data storage. And now we can move to class network at line 449, which is the abstract class for networks itself. And basically, a network is something that has a topology in it, a underscore topology. And this is a private variable because we're going to define a property called topology. And this topology property is going to be the thing that we actually access the topology through. So it turns out right now it really is just, there's no additional logic or checking or anything else, but this is a place where if you wanted to put some kind of checks or delays or whatever, you could potentially. But I really wanted to capture the fact that, hey, this topology field is a dynamic field. It's a property. It's not simply something that's static. And it also provides, a network provides another thing that topology doesn't, namely an inject packet method, because you need to be able to potentially send packets into the network. Not implemented here, because this is where we're defining the idea of a network.
You're going to subclass this?
Yep, we're going to subclass this. You are totally right. We used to have two subclasses, concrete and virtual. Right now Yep.
Now there's concrete.
Now there's just concrete. But we hope to resurrect virtual. There's equality testing, which basically looks at the two networks and checks if their topologies are the same. And there's the ability to copy a network, which does exactly what you'd expect. And we're done with the network thing, the network.py. So now we're going to look at the runtime. And the runtime, which you've already seen the vast majority of, or a lot of at the very least, is the concrete network, starting at segment block, starting at line 1000 roughly. And now we can look at what a concrete network looks like. It descends from network, and it's a concrete network that has a runtime associated with it. So it's actually hooked in. It's something that's able to get information from the runtime and feed stuff back to the runtime, which isn't necessarily the case, say, for a virtual network, if you imagine implementing virtual networks. Maybe it would be, maybe it wouldn't. But so it keeps also track of the next topo, keeps track of the runtime. It has a wait period. So maybe there are a series of changes which are happening very quickly in the network. So we don't necessarily want to cause the runtime machinery to start chugging immediately. So we put in a little wait. It's a hack. But it's not the worst hack in the world. And some, update numbers to know which number topology this is, and a lock, so that way we can kind of thread out and actually detect. So when we get something, we start waiting for the waiting period. But if another change comes in, then we find that out, and then we reset the timer and so forth. And that's something you'll see in the code, some logging and debugging. And inject packet is basically using the runtime. So we take a packet, we use the runtime to turn the packet from a Pyretic packet to a concrete packet, and then we use the runtime to send the packet out. And the runtime send packet, it talks to the backend, which talks over the socket connection. We talked Unix domain socket connection that we talked about yesterday to POX, which then sends it out over the actual wire. So query update, so queue update is, set an update, you sleep for the wait period, and if the update number is, when we come out of sleep, has changed, we just skip it. If it hasn't changed, meaning there have been no updates that have happened subsequent to us, well, then we set the topology to be the next a copy of the next upcoming topology, and then we do tell the runtime, okay, let's handle the network change.
What's the reason for the queue? Like, why don't you just update it?
Oh, immediately.
Yeah.
So basically, if you have
something in flight.
Well, basically, when you first attach the controller to a network, if the network's of any significant size, then you're getting a million different events, each one which is changing the topology. And so then you get this huge number of topologies generated in a very short period of time, and it causes stuff to go kind of crazy.
So okay. This actually reminds me of another question I had.
Sure.
Topology stuff. So you're not using LLDP?
We are. We'll get there.
You are, okay.
You're gonna see that. You're gonna see that right now. You just give me like 1 minute.
Okay, cool.
So we got an update number, whatever. We've got the ability to inject discovery packets. Okay, which does self.runtime.inject discovery packet. Let's take a look at what self.runtime.inject discovery packet. Okay, it does self.backend.inject discovery packet. Okay, well, let's look at what the backend does. And now we're going to move out of core for a second. Oh, that wasn't what I wanted to do, but okay, here we are. We're in backend, and we're going to do inject discovery packet. Oh, what does this do? It does self.send to OF client, inject discovery packet, dpit port. Okay, cool. Well, what does that do? OF client, POX client, inject discovery packet. So if the message is inject discovery packet, then we're going to call OF client inject discovery packet. And what does that do? Well, it says it tries to get the hardware address. So the POX backend also maintains a separate data structure for sanity checking on the ports. And then basically, if it checks out, it creates a discovery packet. And then it actually sends that packet to the switch, whose dpit is switch. And oh, what does create discovery packet do? Well, create does this. It is line 196. And if you look at the POX code, this is a bit ripped off from their code. Yeah. But line 211 basically gives you.
Oh, you have POX client.
Yep, I'm in POX client. Yeah, so if you're doing the screen share with me, then you'll see.
I'm following along now.
Okay.
So you call this?
Yeah, POX client line 196.
But you.
Yeah, we call that. So this is called by the inject discovery packet message handler of the POX backend, which receives that message when the Pyretic backend sends it over the Unix domain socket, which is called by the runtimes inject discovery packet, which is called by the concrete networks inject discovery packet. And this thing at line 211 basically boils down to, hey, we're creating an LDP packet. And there's a lot of work involved, and there's some work involved in that.
Don't you listen for LDP packets?
You have to listen for LD packets, but LLDP packets,
because you're like generating.
LLDP packets don't generate themselves from the ether. They must be sent by someone.
A switch, right?
A switch needs to send them, but how does a switch know to send them?
Think of like packet that's been created by before and pushed into the switch.
Exactly.
And then it is received from the other switches. And the switches that we receive
Yeah.
I just didn't understand how it really works.
Yeah, so this is how POX works as well. Except POX does this really irritating thing where
I never actually knew how it worked. I never knew how it worked. Because like basically you just have this discovery module and you listen for these.
Yeah.
You
don't actually need to use LDP packets to do this. You could do it with some other special packet that isn't used for another purpose. Yeah.
Only needs some like.
What's useful about it is if you're connecting to other switches that support LDP that are outside the network, you'll get some useful information back. And they won't be super confused, and maybe crash by accident because you were doing something really unorthodox. So in general, LDP is what people have been using. There's some problems with it, but this is what it all boils down to. And so now I'm going to back out, go back out of the backend, back into core, into runtime. So basically, we have a mechanism that lets us, in a relatively long series of calls and transfers of information, inject discovery packets from the concrete runtime object. So you're going to see that. On like the very next bit. So we were at line 1000 something. Inject discovery packet 1045. Okay, and now we're going to see exactly where these things get injected. So handle switch join. So handle switch join is called by the backend when it receives a message from the POX client saying, hey, an open flow switch join message has been received. with such and such data associated. And so this is going to get called back through the run. So the runtime hooks that all up, and this method gets called. And so what you're going to do is you're going to say, okay, to the next topology, I'm going to add this switch, and great, that's all I'm going to do. And then there's
topology. So that's the thing that becomes the topology when you update.
Yep, exactly. So we create a next topology, yeah, and we sort of copy things in. And now we're going to do
so it's sort of like atomic.
Yeah, exactly. I want to make things atomic, yeah. Because you don't want to change the topology that's in use by the runtime before you've notified the runtime it's changed, because then things go haywire. So yeah, this is another place where we're kind of dealing with yeah, the inherent asynchrony of the process.
Like each switch has its own information. Like I have connected the network to the controller.
Yeah.
And then it's the responsibility of the controller to send beacon packets, like LLDP packets, through it.
Exactly.
To see the length.
Yeah, yeah. So we're going to see exactly where that happens momentarily. So you get a switch connect message. The switch connect message may have some ports, but when a switch connect message is sent by a switch, the switch then subsequently has to send a whole bunch of port connected messages as well. And so those are handled on line 171. And what we do is, not port, sorry, line 1081, handle port join. And so basically, yeah, first thing we do is we add a new port to the next topology. And then
what is a port join?
Port join means a port has joined the network.
Okay, because like a switch doesn't join. A port joins.
What do we call switch join? Yeah, 1084 handle switch join. We just call it joins.
So
you can call them.
Is it different from port up and port down?
It's a little bit different.
So it's a different message.
It is. You'll see that in a second. So in fact, when you get the port join, it can join and it can be down. So we look at the config or status on line 185.
How
right?
do you get POX give you these are going for POX, right?
Yeah. Oh, POX automatically, like, so you define a handler in POX. So,
oh, okay.
Yeah. You got it. And then we hook all that. So, cool. So basically, if you look over here, if you look at, in line 181, the event provides the switch, the port number, the config, and the status. And what do we do on line 185 is we check the configure status. If neither one reports up, then we're not going to send out discovery packets because we know they're not going to go anywhere. Or at least we expect, if it's supposed configured to be down and it says it's down, we're going to assume it actually is down. Maybe a wrong assumption, but that's what we do right now. Okay, so we can change the code. We can totally change the code. In fact, I would love someone to go over this code and
inject something out there,
fix it. Yeah. So maybe you want to do that. There's certain tests in here that seemed like they were logically unnecessary, but when I disabled them, things went haywire crazy. There are a bunch of problems with this code. This is not great code. I would love to see it overhauled, but before overhauling it, we need to know what it does. So let's finish. So 186 is, hey, we're going to send a discovery packet out this switch and port. Great. Now we've got handle port parts, handle port mods. So if it changes status, goes up and down. And initially I was relying on these to actually change the topology. Now it's kind of, I don't rely to change the topology, but I do update the port objects based on it. There's some fuzzy logic in here. There's port up events, port down events. There's handle link update events that are obviously potentially triggered by.
That's what I'm looking for. That's when your LDP stuff comes back, right?
So LLDP stuff, when you get an LDP message back, that's eventually going to trigger a handle link update. Yeah. Yeah, and so this is where that stuff is, and so basically P1 is going to be self.nextTopo node switch 1, the set of ports, and and
This is
so
where it
forth.
is.
Yeah, so this is where all that crap is.
And all of that, like the last 6 or 8 functions,
Yep.
are things that you register with POX and POX.
They're not things you register with POX. The way it goes is the POX client registers with the POX runtime to receive all this stuff. And when it receives those things from POX, then it sends messages to the backend over the Unix domain channel. When the backend gets them, it calls back the runtime. And the runtime registers the concrete network that's attached to it. The concrete network. Exactly. Yeah. And that's the way it works. You know, it's a little convoluted, but it's not bad. You know, it's basically sensible. And I would love to see as I said, I'd love to see the code overhauled. But at this point, I think you guys have the basic understanding of how this works currently. This is also part of the reason why why part of me is like, yeah, let's just get rid of the backend and the POX client or the Beacon client or the whatever client and just own the whole stack. Because there are a lot of layers where things, kind of go up and go down, which isn't super efficient and makes for more difficult debugging and just code bloat and stuff. And it would be great to just kind of, have this code kind of in the runtime and maybe modularize the runtime a little bit more around that. But so now you understand what a topology is, how to use it, what kind of how data structure is set up, what type of cool libraries are available for manipulating it, how it fits into a network, what a concrete network is, and what it provides in addition to the basic network abstraction, and how that concrete network is hooked into the runtime, and the runtime is hooked into it. And all of that is hooked into events flowing from the backend. So the reason why the concrete network has a copy of the runtime is so it can say report, hey, I've changed. And the runtime creates the concrete network instance. So it knows where the concrete network is and can say, hey, whenever I get a handle switch join event, for example, I'm going to call self.network, my copy of the concrete network, .handle switch join. And there you go.